Next up is oral presentation 20, Galloway, New Jersey, Stockton University, Team 2. It's a Mission 12 flight experiment.
Good morning. My name is Daniel Schneider.
And I'm Christina Talone.
We are from Stockton University in Galloway, New Jersey. We're here with our mentor, Dr. Pamela Cohn, and we're going to be discussing our Mission 12 experiment, the effects of microgravity on pegma-based self-assembly and its impacts on drug delivery. So kind of to give you a background about where this experiment comes from, in recent years, controlled release pharmaceuticals have been on the rise. There's a number of inherent benefits from using that over other drug delivery methods. And our research wanted to advance that field a little bit and kind of address some of the issues we were having, that the field is having, Specifically, we're going to be looking at hydrogels. Hydrogels are a polymer gel saturated with and by mass mostly water. As a result of their composition, they are inherently non-toxic, and they can be ingested, injected, and planted in the human body safely as a controlled release for different types of pharmaceuticals. But what makes it so great also makes it causes it to have some certain drawbacks. So while the hydrogels are mostly comprised of water, they do very well at dissolving hydrophilic drug molecules that are drug molecules that dissolve well in water, obviously. Those hydrophilic molecules integrate well into the hydrogel and then deliver at a nice consistent rate when implanted in the body. However, hydrophobic drug molecules, those which do not like water and are not water soluble, they tend not to integrate well into hydrogels, and if they do, tend to leach out and deliver at an inconsistent rate. So the idea we kind of came up with is to encapsulate these molecules, these hydrophobic molecules, in a polymer micelle. And basically what that is we'll have a hydrophobic molecule, which Christina will get into exactly what the chemistry is and how the system is going to be built. But we'll place hydrophobic molecules in with a polymer, and the polymer is allowed to self-assemble in basically an encapsulation around that molecule. That molecule then has a vessel in which can then be integrated into the hydrogel. It works on Earth, however, there's a phenomenon known as polydispersity, and you can see on both slides how all the different micelles are shaped, different sizes and different shapes. Because of this polydispersity, it will integrate into the hydrogel, but it won't deliver at a consistent rate, essentially creating the same problem we started with. So our hypothesis is, under microgravity, the only outside force acting on these molecules are going to be surface tension, and that pegma, which is our polymer of choice, and indigo dye will self-assemble with a high level of monodispersity, meaning all of the micelles take up similar shape and size. We hope to see that this leads to superior controlled release of those dyes, and if it does, it may open the door for many different classes of medications to be integrated into these hydrogel systems.
So we are using a type 3 FME, which allows us to have 3 different chemicals. So in our first one, we'll have an aqueous solution of indigo, and that would be indigo dye dissolved in water. And the reason we're using a dye in place of a drug is that we'll be able to see it when we analyze it. We'll be able to see the blue in the pictures of the hydrogels, and also as it escapes from the hydrogel as if it were going to be used as a drug delivery system. In the second, we have our polymer pegma and the individual molecules, and those are dispersed in DMSO. And in the third, we have aqueous peg dithiol, which will act as our crosslinker. For experimental design, this is how it launched this morning with all 3 components separate. And then 2 days after the arrival, we will have clamp A be released and gently shook, and that will allow the polymer to encapsulate the dye, and this was through self-assembly. Now, on the ground, we'll see polydispersion, as we were talking about, all different shapes and sizes. You can see them forming on the right, and that's because they have gravity acting on it as it self-assembles around the dye. But on the ISS, we will expect there to be monodispersion because of the lack of gravity, and thus they will be all the same size. Then we will have clamp B be released 5 days before coming back to Earth. And this is going to introduce the crosslinker into the solution. And what the crosslinker is going to do is harden the polymer shells that we had just formed. So this is going to ensure that they maintain that shape that they had just self-assembled in each environment. And this is especially important for the microgravity, so it maintains that shape that was formed in the microgravity on the ISS, and it will maintain its shape as it re-enters the atmosphere. For analysis, we're using an atomic force microscope, which will produce images of our hydrogels within fractions of a nanometer. And then we will use a computer software, which is ImageJ, and this will analyze our image and calculate the dispersity of the system, which is what we're interested in finding out. And then we have thermogravimetric analysis, and this will show us how the drug molecules would release if they were in the human body at the human body temperature. And then we'll also be using dynamic light scattering, which is another method of measuring the distribution in size of small particles. So thank you guys for listening. I'd like to acknowledge Dr. Hartman and Dr. Schulman for helping us with microscopy at Stockton, and also Dr. Nucci from Rowan University, and of course all our community partners. Thank you.
Hi, my name is Garth. I'm from Stamford, Connecticut. So in your experiment, you used crosslinks to help harden the shell for the polymers. So if you were to use to use this practically on Earth, would you send it up to space, have the polymers hardened in space, crosslink them, and then send them back down to Earth? And would that be usable? Would that be an effective way to create it, or would the crosslink mess with some kind of property of the gel?
Are you talking real world app, if
Yeah.
this was serious? So the crosslinker really, for our purposes, is only necessary really in the microgravity experiment to survive reentry.
Okay.
The polymer itself is actually rather fragile. So if we were able to somehow mimic microgravity on Earth, then we wouldn't need that crosslinker. The crosslinker makes it very hard and makes it very difficult to break it out of that shell. If this was applied medically somehow, we wouldn't be using this polymer probably. However, a crosslinker probably won't be needed.
Okay, thank you.
Your turn.
Hi, I'm Vedant from Stamford, Connecticut, and I kind of have two questions actually. So I know you already kind of addressed why you didn't use a drug and you used indigo instead, but would it have been better to use a drug to simulate what it actually means to inject pharmaceutical drugs into the human body in microgravity situations?
Yeah, in our case, where we're concerned about the dispersity of it, all it matters is whether it's hydrophobic or hydrophilic, and our drug was the right choice for that. That would mimic those kinds of drugs that cannot be used in this system, but we hope could.
Okay. And also, the second question. So the polymer structure that you used, was it PEGMA? Was that what it's called? Does it have any any effects on the human body, symptoms per se? Because you mentioned it being used for pharmaceutical purposes.
So PEGMA is the SDS sheet. There's no health hazards. Obviously, I'm not going to say I'm a doctor and say put it in your body, but this polymer is really just an example.
Okay.
We wouldn't necessarily be using this specific polymer for medical applications. We're interested in really just finding out how that self-assembly process works, more
Okay.
so than this specific polymer with this specific dye.
All right. All right, thank you guys.
Mm-hmm.
Hello, my name's Ron from Wisconsin. So you mentioned using micelles, which I'm not sure how big they are, but using smaller particles like nanoparticles where maybe gravitational effects are null. So what made you choose using a delivery system with something bigger, like a micelle, versus something smaller, like a nanoparticle?
Well, we will have the bigger micelles also, but there also may be microgels that have formed that could benefit from that as well.
Oh, okay. Thank you.
My name is James from Stamford, Connecticut, and you guys mentioned polydispersion on the ground truth experiment. It was in different shapes due to gravity's force. Is that the only factor you found for the different shape? Gravity's the only factor?
Well, I guess our hypothesis is that's what we're hoping is the reason for polydispersity. When we were designing this experiment, well, more even before that, when we were coming up with ideas for what this experiment was, we actually found a study that used a very similar system to this, and they couldn't account for polydispersity. Their polydispersity was almost like a side effect, I guess, which is why they couldn't use it for these kinds of applications. And then we took that, well, perhaps its gravity has some sort of impact. And now we're going to explore that. Now, if it comes back and it still has that polydispersity, then we would have to look into why exactly did it happen that way, and gravity must not be the reason.
Thank you.
Thank you, great job.